All right, now we're ready to cover the second part of Chapter 2 on water. This time we're going to discuss the chemical properties of water. So we're going to talk a little bit about three different topics: the ionization of water and pH. Then we'll discuss acid-base reactions and some calculations for that. And then finally we'll talk a little bit about buffers. So first, when we consider water in just pure water sitting around, water is going to react with itself. So some water molecules will transfer protons to each other. This reaction is called autoionization. So in a liquid solution, we have water and water. You can take one proton away from one of the water molecules, give it to the other, and then you'll end up with one hydronium ion, H3O+, and one hydroxide ion, OH-. And so this is a chemical reaction, and like any chemical reactions we've discussed, it's going to have an equilibrium constant. And the equilibrium constant for pure water is Kw, and that's just the concentration of the hydronium ion times the concentration of the hydroxide ion. So it's essentially the product side of this reaction. This is partially because we tend to ignore liquid water. So the reactants are liquid water. We don't need anything in the denominator of this equilibrium constant. So how much is water going to autoionize? How much is water going to start pulling protons off of itself or its neighbor molecules? So in standard conditions at 298 K, the value of Kw is 1 × 10⁻14th power. And we already know that Kw is equal to concentration of hydronium ion times concentration of hydroxide. And that value is, again, 1 × 10⁻14th. So if you want to break that down further, we can consider that the concentration of hydronium ions is always equal to the concentration of hydroxide ions in pure water, because one water molecule is always pulling the proton off of another neighboring water molecule. So those species will always be equal to each other. And so they're present in the same amounts. And so to get the concentration of either one, you can take the square root of Kw. So the square root of 1 × 10⁻14th, the -14th power, equals 1 × 10⁻⁷ power. So when you consider that, then we can figure out that in pure water, the concentration of hydronium ions equals the concentration of hydroxide ions, which is equivalent to 1 × 10⁻⁷ molar, or moles per liter. So to bring that a step further, now we can know how to calculate the pH. And the pH of any solution is calculated with the equation pH equals -log of the concentration of hydronium ions. It's often written as a sort of shortcut to take away the water from the hydronium ion, because you can always sort of ignore water, and when you take away water from there, you end up with just protons. So pH can also be written as -log the concentration of protons in a solution. In a real life solution, you would never have just protons swimming around by themselves. They're always attached to a water molecule. That's why it's more correctly written as the concentration of hydronium ions. So in pure water, if we wanted to calculate the pH, we already know that the concentration of hydronium ions in water is 1 × 10⁻⁷ power molar. So if you wanted to figure out the pH of water, we would take the -log of 1 × 10⁻⁷ molar, and we would get exactly 7. So a lot of times, especially in biochemistry, we're not just talking about water when we're trying to calculate the pH. We're often discussing acids and bases that are in aqueous solutions in water. So just as a reminder, we're going to be considering the Bronsted-Lowry definitions of an acid and a base. A Bronsted-Lowry acid is defined as a molecule that donates a proton. A Bronsted-Lowry base is a species that accepts a proton. So when you place a Bronsted-Lowry acid or a base into water, it will ionize. It will either donate or receive a proton. So a Bronsted-Lowry acid is in red at the top. When you add that to water, you end up with a hydronium ion because the water accepts the proton from the proton donor, the acid, and then you're left with the conjugate base. Sort of the reverse of that is the Bronsted-Lowry base. You place the Bronsted-Lowry base into water. The base acts as a hydrogen acceptor from the water, so you have the conjugate acid and a hydroxide ion. When we often have to consider the relative strength of acids and bases. So some acids, when they're placed, and bases, when they're placed in water, will completely dissociate. The protons will fully dissociate from the conjugate base in the case of an acid, or the hydroxide ions will fully dissociate, the base will fully accept all the potential protons and become fully conjugate acid. So that would be a strong acid or base. But a lot of times we also have weak acids or bases where you only have partial ionization. So to figure out if you have a stronger or weaker acid or base, you can consider the Ka or the Kb, the equilibrium constant. And the equilibrium constant in the case of an acid, shown at the top, is, like many of the other equilibrium constants we've talked about, the concentration of the products divided by the concentration of the reactants. And here, as per convention, we exclude the liquid water. So we have the hydronium ion and the conjugate base as the numerator in this equation for the Ka, and the weak acid as the denominator for the Ka. The larger the Ka, meaning the more shifted it is towards the product and the conjugate base, the stronger the acid. Very similarly, when you want to calculate the Kb, to figure out the relative dissociation of the base when it's added to water, you once again look at in the numerator we put the products, the conjugate acid with the hydroxide ion, and in the numerator we put the base, the Bronsted-Lowry base. So once again, the larger the Kb, the stronger the base you have, because the more product you have, the more conjugate acid you have relative to the base you started out with. So when we want to calculate the pH of a solution for a strong acid, it's relatively straightforward because it will become fully ionized, and similarly for a strong base. So first we'll consider the strong acid. So for a strong acid, all the protons are fully removed from the acid, and so the concentration of protons in solution is equivalent to the concentration of acid that you added. So for example, a strong acid, hydrochloric acid, all of the protons will dissociate from the chloride ions, so you have the concentration of hydrochloric acid that you added is going to be equivalent to the free protons that will dissociate when the acid ionizes. And so to calculate the pH from there, you can straightforwardly use the equation that we mentioned, which is minus log of the concentration of protons. For strong bases, it's similar, except this time instead of considering the concentration of protons that dissociate, you consider the concentration of hydroxide ions that form. So one example of a strong base you might see is sodium hydroxide. So the concentration of sodium hydroxide that you add to a solution is the same concentration of the hydroxide ions that will dissociate, because it's a strong base, so it will fully ionize. And similarly, you can calculate the pOH by taking negative log of the concentration of those hydroxide ions. So how are pH and pOH related? pH and pOH always add up to 14. And the way you can remember that is the sort of pH scale goes from 0 to 14, and so the pH and the pOH added together will always get you to 14. For pure water, like we considered before, the H and the OHs kind of add together and they're equal, so the pH 7, as we discussed, and the pOH would also be 7, and those add up to 14. So for weak acids and bases, calculating the pH is a little bit more complicated. As a sort of shortcut or approximation, during particular conditions, you can use these sort of simple equations. So if you assume that the concentration of the acid or base is very high comparatively, and the Ka or Kb is very low comparatively, you can calculate the pH of that solution using, for an acid, pH equals minus log of the square root of the concentration of acid times the Ka. Similar but different for the base. For the weak base, you can calculate the pH equals 14 plus log of the square root of the concentration of base times the Kb. And this can also often give you a very good idea of the pH of the solution, but it's not always exactly correct, and it's very hard to sometimes know whether you can make those assumptions. How do you know if the concentration is high enough? How do you know if the Ka or B is small enough? So the quote-unquote real or correct way to do it is to set up an ice chart, which I'm not going to go through right now, but which you may be familiar with. So to move on from there, the reason we're kind of interested in talking about acids and bases dissolved in water is because in a lot of biological systems, buffers are very important. So rather than how you may have thought about acids and bases before as components that might intentionally change the pH of a solution, in the case of a buffer, you create a buffer because you actually want to try to keep the pH fairly constant within a narrow range. So there are several important buffers or buffer systems biologically that help to keep that particular compartment or area at the particular pH that it needs to be to function. So what are the components of a buffer system? Fairly simple. A buffer is usually a solution in water that consists of a weak acid combined with its conjugate base. So the two of those components acting together help to buffer the pH, to kind of keep it constant, even when you add acid or base to that solution. So how does a buffer do that? Well, for either direction, so starting with this first example, if you tried to add a base to your buffer, the weak acid that's present in your buffer as one of the components will help to neutralize the base that you add. Similarly but different, if you try to add an acid to your buffer, the conjugate base that's present, the weak base, will neutralize any acid that you add. And this is true within a relatively narrow range of pH that's different for each buffer, depending on the exact buffer components, the exact weak acid and weak base. And so that's the components of a buffer that helps to resist those changes in pH. So first of all, how can you calculate the pH of a buffer? We use the Henderson-Hasselbalch equation, and that is written here. So the pH of a buffer, you start with the pKa, and then you add the log of the concentration of the conjugate base divided by the acid. So how would we know what the pKa is? So for a buffer, we've discussed a couple of slides back how the Ka describes the relative amount of the conjugate base to the acid. For a buffer system where you have both the acid and its conjugate base, at that midpoint where sort of half of the protons are dissociated, you have what's referred to as the pKa, and the pKa is the pH at which you reach that midpoint. And the equation that you can use to calculate the pKa, if you have a known Ka, is written here. So the pKa is equal to negative log of Ka. So for these three different buffers shown in this graph, they each have three different pKa's. At the top, we have this buffer system with ammonium and ammonia with the loss of a proton. And the pKa here is a little bit above 9. And the buffering, and it's able to be a buffer within about 1 pH unit away from that pKa. So a little above 9 to a little above 10, and then from a little above 9 to a little above 8. So within that pH range, this buffer system resists changes in pH, and you can see that this graph of pH sort of flattens out and becomes relatively horizontal in this range. Once you reach outside of this buffering range, if you add too much acid or too much base, it sort of overcomes the buffer's ability to counteract that added acid or base, and that's when you see these lines start to become much more steep because the system is no longer able to act as a buffer outside of that pH range. And different buffer systems have different ranges of pH at which they're able to act as a buffer. So this next example shown in the middle in this sort of beige pink color is showing dihydrogen phosphate as a buffer system, and that the pKa there is a little bit below 7. And then on the bottom we have acetic acid, and the buffer range there is shown in green, and the pKa there is a little bit below 5. So each of these buffers is really, really good at maintaining a certain pH range, and that can be helpful in particular systems where you're trying to have reactions or other processes that need to be at a certain pH in order to proceed. So if you recall, our example in the middle there was dihydrogen phosphate as a buffer system. This buffer, or this molecule, can actually have multiple protonations and deprotonations. And so it's what we call a polyprotic acid. So there are some species that are shown here that are what we call amphiprotic. So an amphiprotic species is one that is able to both donate and accept a proton, so amphiprotic, and that's very similar in the context we're talking about here to a species that's amphoteric. And a species that is amphoteric is able to act as both an acid and a base. So here, where we're talking about Bronsted-Lowry acids and bases, a Bronsted-Lowry acid is a species that donates a proton. A Bronsted-Lowry base is a species that accepts a proton. So here, amphiprotic and amphoteric are almost interchangeable in the context of Bronsted-Lowry definitions. So here we have this polyprotic acid. So we start with phosphoric acid, H3PO4. When it loses a proton, it becomes dihydrogen phosphate, H2PO4-. That can lose another proton and become hydrogen phosphate, HPO4-, which can finally lose another proton and become phosphate, PO4-. So this one type of acid and conjugate base can have these 4 different forms, and these 2 forms in the middle, the dihydrogen phosphate and the hydrogen phosphate, if you go towards the left, they can accept a proton. And if you go towards the right, they can donate a proton. So these 2 species in the middle would be considered amphiprotic, and because they can act as either an acid or a base, they can also be considered amphoteric. And they also make a special sort of buffer because you can end up having one type of molecule that will give you three different ranges of pH at which it can act as a buffer. So here at this first, so you have three different pKa's where the two types of species are equal to each other. So the first one is equal amounts of phosphoric acid and dihydrogen phosphate. Second one is equal amounts of dihydrogen phosphate and hydrogen phosphate. And the last one is equal amounts of hydrogen phosphate and phosphate. And so within one pH unit of these three pKa's, you have sort of three different pH ranges where these species can act as a buffer. So that brings us to our sort of real-life example, the buffering system that's present in our blood. So our blood is a buffer. It contains the acid and the conjugate base. The acid is carbonic acid. The conjugate base is bicarbonate. Another name for bicarbonate is hydrogen carbonate. So the way that we end up with this buffering system in our blood is we start with the carbon dioxide that we get from the air that we breathe. So the carbon dioxide gas gets converted to dissolved essentially in water to become aqueous CO2. That CO2, when you add more water, can be converted to carbonic acid. That carbonic acid can then dissociate to form bicarbonate and a proton. And so, depending on the amounts of reactants and products that are present in the system at any one time, you can end up with a particular equilibrium that will have a particular pH, depending on, for example, the concentration of protons in the solution, which, as you know, is one way to calculate the pH. So the overall equation for these processes all added together, you have carbon dioxide gas plus water, can form a proton and bicarbonate. And so this is that buffering system that helps to keep your blood at a very narrow range of pH, and that your blood needs to be at that pH to keep you healthy, to keep all of your enzymes able to catalyze reactions at the proper rate, to make sure that proteins can keep their shape and perform their function to keep you healthy. So normal blood has a very, very narrow pH range of only 0.1 pH units. Normal blood should have a pH between 7.35 and 7.45. When you're in acidosis, the pH drops to between 7.1 and 7.35. When you're in alkalosis, the pH is too high. You're between 7.45 and 7.6. So ways that blood can fall out of the normal pH range can be for two main reasons. So the first is a sort of metabolic reason. Maybe you took a drug or some other substance that affects the buffering system in your blood and alters that balance of protons and bicarbonate compared to the carbonic acid. Or the other reason is actually your breathing rate, because the source of that CO2 is from the air that we breathe. So now that we've discussed a lot about the chemical properties of water and pH, please go ahead and answer some of those practice questions from the Chapter 2 Chemical Properties of Water document. Thank you.